Hello everyone, thank you for being here today. My name is Juan Ramirez and I will present the work I have done together with Jose Gallego-Posada and Akram Erraqabi from Mila and Université de Montréal on flexibly learning sparse neural networks with constrained OCR regularization. Neural networks can scale to billions of parameters. Training, storing, and deploying them is expensive, but there is also the need to work with them efficiently. And we want to do this without disregarding performance. Fortunately, the performance of neural networks has been shown to be robust to harsh levels of parameter pruning. Han et al. Managed to prune a BGG16 to 4% of its original size without increasing error. One way of making them more efficient is by training them to be sparse in terms of the LCR norm of their parameters, here denoted by theta. The LCR norm effectively counts the number of non-zero entries in theta. Consider a supervised learning task. The empirical risk can be augmented with a term penalizing the LCR norm of the parameters, given a suitable penalization coefficient lambda. Sadly, the LCR norm is non-differentiable. But Luzos et al. Propose a reparametrization of theta, which alleviates this problem. Let theta be a theta tilde, which are free parameter magnitudes, multiplied with a set, which are stochastic gates, indicating whether a parameter is active or not. A natural choice for set is a Bernoulli distribution, but this does not solve the non-differentiability problem. Rather, they employed a mixed concrete distribution which has point masses at 0 and 1, but also a density in the interval between them. The optimization objective is reformulated as its expected value under the gates of the new parametrization. We consider this reparametrization but formulate a different optimization problem. We minimize the empirical risk f, subject to the L0 term g being below a threshold. Also, the total number of parameters is added as a normalization term in the constraint. As such, this epsilon hyperparameter represents the maximum proportion of active gates we want. Note that this constraint problem is different to the penalized problem. Penalization aims to minimize both terms f and g, given a relative priority of lambda. The constraint formulation, on the other hand, wants to find the best model in terms of f, which satisfies the sparsity constraint. Now, in order to solve this problem, we consider the Lagrangian associated with the optimization problem, and then its min-max gain. We choose to optimize this with gradient descent on the model and gates parameters and ascent on the multiplier. So let's take a quick look at how this optimization behaves on MNIST classification with an MLP. We are looking at the constrained L0 term, the Lagrange multiplier, the training loss, and the validation error. Initially, the training loss and validation error decrease, but sparsity is not a priority. This happens as the multiplier is initialized at 0. Then lambda increases, model density is decreased, and this also leads to an increase in validation error. At around epoch 100, the constraint is satisfied and then the multiplier starts to decrease. Constraints can be liberating as they can represent gains in interpretability, flexibility, and accountability. The constraint level has clear semantics. It's the maximum we want the constraint function to reach. And one could define this from the quantity of resources available. Constraints also contribute to flexibility. In order to get a satisfactory density level, when applying the penalized approach, one needs to tune the penalization coefficient and potentially run several experiments. This challenge grows more when introducing various sources of regularization. Lastly, constraints convey a clear, transparent understanding of what a satisfactory model is. So constraints can provide some benefits, but do these deteriorate performance in terms of ERM? Well, we compared some experimental results with those of Luzos et al. When performing MNIST classification, and we found that we could achieve similar levels of sparsity and error. This approach is not universally better to penalization, but it can add flexibility without compromising predictive performance. Thank you all very much for your time, and we hope to see you at the poster session.
This is asking for all the authors in general. So how do you leverage the practical usage of the problems that you are solving with the chosen model?
Actually, if I understand the question correctly, in our case, we have to go a different route because our problem specifically, we target a more theoretical problem in terms of how to train a model which is sparse and how to do it in a flexible way. So if we could follow up that question to something that would be a bit more applicable to perhaps our case, would be great.
Yeah, I feel that I don't know if this question is maybe intended to works that are a little bit like more theoretical. Like I don't know, in my sense, I feel that I do a very applied um, work with trying to identify and track trolls, internet trolls. Yeah, that's just my opinion.
Yeah, same thing from us from the pharmacovigilance paper. I mean, the model itself didn't really matter. I mean, it's just, the combination of how you get the data, how you frame the question, and, the model itself is just a tool to get something out of it. But we could have tried, anything from a very simple model to a very complicated model. But, I think the end goal was a little bit something that would have come out anyways with, any model we would have tried.